Okay, YouTube, this is my next video on graphing inequalities in two variables, in which we're going to focus on what we refer to as graphing systems of linear inequality. So recall that previously when we talked about systems of equations, we had these things that were equations. So maybe in this form ax plus by equals c, if I'm just going to play with the alphabet here, we say dx plus ey equals f. We could solve a system of equations if they had a solution that was in common. And so at least with respect to their graphs, perhaps we had two lines that ran into each other at a single point. We would say with respect to their equations, then their common solution would be their point of intersection. So a solution to a system, remember, is a solution xy to all of the equations in a system of equations. Well, we're going to say very much the same thing or a similar thing to systems of inequalities, except for that we say that the solution set of a system of linear inequalities in two variables is the set of all ordered pairs that satisfy each inequality in the system. So again, whereas equations might share one common solution, remember that inequalities, okay, if we were to change these to say some inequalities, then what we would have gotten really is just some shaded half planes here. And what we're looking for is the part where they shade together or intersect. So we say that thus, okay, to graph a system of inequalities in two variables, what we do is begin by graphing each individual inequality in the same rectangular coordinate system. Then we find the region, if it exists, that is common to every graph in the system there. We say that this region of intersection gives us a picture of the system's solution set. And so with respect to what we're finding here, kind of squeeze this in here, we would say that if we were to graph linear inequalities, say that we have a linear inequality 1 and a linear inequality 2 here, if I were to say have one that shaded this way, okay, this way, and one that shaded, say, also this way, then you could see that the point or the region that they have in common right here would be this part down here where they both shade together. And so this is going to be what we call the solution region for our problem here, or for our system, okay? But we also call this the feasible, F-E-A-S-I-B-L-E, the feasible region. And the feasible region contains all points that satisfy all of the inequalities in the system. So to graph the solution set to this system here, essentially, the very first thing we would do is go ahead and replace these inequalities with equal signs and graph these as if they were equations. So 2x plus 3y is equal to 12 here. As we graph these, let's go ahead and do the intercepts. Since these are both in standard form, we'll say here are the intercepts of our first line here. And so if we plug in 0 for x, okay, we get negative y equals 1, or in other words, y equals negative 1. And if we plug in 0 for y now, okay, in the first equation, then we would get x equals 1. And so we'd say x equals 1 here. Those are our two intercepts there. So to graph this one, we would say that it hits at 0, negative 1, or a y-intercept of negative 1, and an x-intercept of positive 1. And so this line, since we're graphing the first one here, we would want to graph this with a dotted line. And so to go back, let me do this also. I'm going to put open dots here, open dots, because they wouldn't actually be a part of the solution set. We're going to put a dotted line through these, okay, and make sure that we label it. So to label this, we would say that this is x minus y equals 1. Now with respect to our second equation, if we're going to find its intercepts, let's plug in 0 for x and y respectively, find our intercepts. So plug in 0 for x, we get 3y is 12, and that only is true if y equals 4. And plugging in 0 for y, okay, we get 2x is 12, meaning that x is equal to 6. So our y-intercept is 4. 1, 2, 3, 4, and because it's an or equals to here, I'm going to go up 4, I'm going to draw a solid dot. So we get a solid dot, 0, 4. And then at 6, 0, we go 1, 2, 3, 4, 5, 6. That's our x-intercept here. We'll go ahead and draw a solid line through these 2 points right here. So a straight edge if you've got one. If not, just go ahead and draw it through. And what we're going to do is going to make sure we label this 2x plus 3y is equal to 12. And so with respect to where these things shade, that's going to be what we do next. So in terms of what we've done, all we did was graph and label both equations. Now what we're going to do is go back and test points. So when we test points, we're going to choose points that are not on either of these equations. And so we could see that 0, 0 is on neither of these. So our most convenient candidate is to test 0 and 0. So with respect to our first equation, we have x minus y is less than 1. If you plug in a 0 and a 0, we get 0 is less than 1, which is true. So with respect to our first equation, now which one was that? Well, see how we labeled it? It was important that we did because we're seeing that 0, 0 is on the above side of it, and it was true. So we're going to shade all points above this. And the way we're going to do this is, unless you have colored pencils and you sketch lightly, we're just going to put in all these arrows that indicate we're going to shade above the dotted or dashed line here. So to test 0, 0 on our other line here, in our other inequality, we had 2x plus 3y is greater than or equal to 12. So to look at this here, we'd say 2 times 0 plus 3 times 0 is greater than or equal to 12. In other words, 0 is greater than or equal to 12, which is a false statement. So since this is false, that means that with respect to this other equation, this 2x plus 3y equals 12, we're going to shade away from 0, 0 to the side not containing 0, 0 because 0, 0 is not a solution. So when we look at the solution region here, which is what we want to find, we say that it's this region up here where these two graphs shade together, because this would be all the parts or all the points x, y that would make them both true. So one thing that we want to make sure that we clearly identify here is that this region has one vertex. And I'm going to put clearly here an open dot right there, because we would say that even though we contain all of the points that are actually on 2x plus 3y is greater than or equal to 12, we don't contain the points that are on this line that is dashed. So we can't say that where these two lines intersect is a solution, because it's only a solution to our second inequality and not our first inequality. So what I want you to do is to graph both of these as if they're equations, okay? And then make sure you label them, but go back and test some points and find the common region where they shade together, or our solution region. So we say solution region, or our feasible region is this point where the arrows all shade together. Cheers.